Hi everyone. In yesterday's lesson we learned about what similar polygons are, and our next step over the next couple sections we're going to focus on triangles, and we're going to go back to proofs. We're going to talk about how to prove triangles are similar. So let's start with a quick summary of yesterday's lesson. We said similar polygons are shapes that are exactly the same except maybe different sizes. Maybe you have like a big version and a small version of the same thing. So as I was saying, for the rest of Module 3, we're going to focus on triangles instead of polygons. Instead of 4, 5, 6, 10-sided figures, we're going to make it simple and focus on 3 sides, triangles. And our goal is going to be to prove two triangles are similar. So we did proofs back in book 1, in the Math 1 book. We did proofs of how triangles are congruent. Now we're going to prove that triangles are similar. Now, the first way to do that is using angles only. So we know that if the triangles are similar, the angles are congruent. That actually works backwards also. So if we can show the angles are congruent, it means the triangle is similar, the triangles are similar. And also, based on something we learned earlier this year, you really only need to show 2 of them. And the reason for that is that if two angles of 2 triangles are the same, the third one will automatically also be equal because you have to subtract from 180 to find them. So I mean, if you just think about it for a second, if you got 2 triangles and these two angles of each one are the same, and you add those both up and you subtract from 180 to find the third angle, it's going to be exactly the same. So that gives us our theorem. We're going to go back to those letter theorems, kind of like when we did congruence, except this is one that didn't work for congruent. If you remember when we were trying to prove 2 triangles were congruent, we said AA or even AAA doesn't work. And this is really the reason why. Because we said if 2 angles of one triangle are congruent to 2 angles of another triangle, then those triangles are automatically similar. Not congruent, similar. So let's do an example right here. We have these 2 triangles. We have kind of like that bow tie picture. We have 2 triangles meeting point to point. And I marked one angle in each triangle 81 degrees. So I said, are these 2 triangles similar? Do we have enough to say 100% sure they're similar? Yes or no? So I look at the picture and I say, well, one of the angles is the same in both triangles. They're both marked 81 degrees, so those angles are congruent. And then I remember, oh yeah, back when we did our congruence proofs, when you have that bow tie picture where 2 triangles are meeting point to point, you get what are called vertical angles. So I'm going to mark this angle here congruent to this angle here because those are vertical angles. Now we can say, yes, I can say definitely 100% these 2 triangles are similar. Reason? By angle, or AA. And that's all you need to do for similarity. If I can show 2 angles of one triangle are the same as 2 triangles of another, you don't need to know anything else. That's enough to say that the triangles are similar. So that's what we call the angle-angle similarity postulate, or we're just going to call AA from now on. Okay, now there's another. It's actually presented as in the book as a theorem, but it's really more of a concept I want to explain to you. If you have a triangle and you draw a line down the middle of the triangle that is parallel to one of the 3 sides, anyone, it doesn't matter. What it does is it creates 2 similar triangles. So here's a picture. We have the big triangle, which would be like KHJ going around. And then you have that line going through the middle, LI, that is parallel to KJ. I put the little arrows on it to show they're parallel. And what that means, I'll highlight them in color to show you. This red triangle here, this smaller one, which would be LHI, is automatically similar to the big triangle right here, the blue one now, KHJ. Now the reason for that is something we learned back in book 1 again about parallel lines. if you think about our parallel lines, by corresponding angle postulate, this one is congruent to this one, and this one is congruent to this one. And there's your AA. So again, we're using things we've learned earlier in class. And again, you don't really need to know that. I was just kind of showing you where the theorem came from. But if I take a triangle and I draw a line through the middle that's parallel to any one of the three sides, actually, it always creates similar triangles. So let's turn that into an example. I'm going to use the same picture, and I'm going to say HI is 4. Let's mark it in the picture. HI, so this one here is 4. LK, this one down here is 5. And IJ, this one over here is 10. And we want to find XL. This is the question mark right here. Now, eventually, with enough practice, you'll be able to do the question just by looking at it. But what I'm going to do right now, since this is brand new to us, it's kind of hard to see when there's a triangle inside of a triangle, so I'm going to redraw the two. I'm going to say, first of all, here's the small triangle on top, and it has the question mark here and the 4 here. And here's the bigger triangle, but without the line through the middle. Now, this is where it gets a little tricky. What I'm going to do, instead of a question mark, I'm going to call this one X. Because when you're doing the big triangle, if I want to figure out how long that side is, I have to add these two things up. So this side right here is X plus 5. And this side over here is 10 plus 4, or 14. So now, by redrawing the two triangles separately and realizing, okay, the top one was easy. You have an X and a 4. The big triangle, you're not using 5 and 10. You're using 4 plus 10 for one side and X plus 5 for the other side. Once you get that set up, though, now all of a sudden it's just like our question from yesterday, actually. I'm going to match up sides. I'm going to say this side here matches up with this side here because these are similar shapes. And this side here matches up with this side here. So let's set up a proportion. Let's do X over X plus 5 equals, and then in blue I had 4 over 14. Now, just like yesterday, if you want, you can reduce the 4 over 14 to 2 over 7. That might make it a little bit easier. So then my question would say, let me move over here where I have a little bit more space to work. X over X plus 5 equals 2 over 7. I divided the 14 and the 4 by 2. Now you can cross multiply. So I have 7 times X equals 2 times X plus 5. Let's solve for X. 7 times X is 7X. On the other side, you have the distributive property. 2 times X plus 5. 2 times X is 2X. Plus 2 times 5 is 10. Okay, let's get rid of the 2X. So I'm going to do minus 2X on both sides. Put my little dotted line in there. I like to do that. 7X minus 2X is 5X. We still have a 10 over there. Divide both sides by 5, and what we just figured out is X equals 2. Now remember, as always, go back and double check. I didn't say solve for X. We're not done. I said find HL, which was our question mark, which is X. So we are done. The way we set up the question, I made X what we were trying to find. So now we're done. X equals 2. But again, the question itself was a problem we already did yesterday. It's using proportions and using similarity, but the setup was different. Instead of the question as we drew it, like this, where you see two separate triangles, that was yesterday's problem. Today is seeing the triangle inside the triangle, being able to separate it and create that problem and solve it just like yesterday.